Quantum physics challenges our intuitive understanding of reality, particularly the notion that you can't get something from nothing. In the seemingly empty vacuum of space, the manipulation of nothingness can actually cause particles to materialize. This counterintuitive phenomenon occurs at the subatomic level, where the rules of classical physics give way to the bizarre behavior of quantum mechanics. When particles collide in empty space, they can produce additional particle-antiparticle pairs, seemingly out of nowhere. This process is a fundamental aspect of quantum field theory. Even more intriguingly, when we attempt to separate a meson's quark from its antiquark, new particle-antiparticle pairs are pulled from the apparent emptiness between them, demonstrating the dynamic nature of what we perceive as nothing. The Schwinger effect, a remarkable prediction made over 70 years ago by Julian Schwinger, one of the founders of quantum field theory, further illustrates how the universe can create something from nothing. This effect posits that a sufficiently strong electromagnetic field can spontaneously create particles and antiparticles from the vacuum itself, without any initial particles present. For decades, this remained a theoretical concept, believed to require enormous energies only achievable in extreme astrophysical environments or high-energy particle physics experiments. However, in a groundbreaking development, researchers recently verified this effect in a laboratory setting using the unique properties of graphene, bringing this abstract concept into the realm of observable phenomena. Modern science has revolutionized our understanding of the universe's fundamental nature. Rather than a collection of static objects floating in empty space, we now recognize the universe as a complex interplay of dynamic quantum fields. These fields permeate all of space, harboring latent energies and potential for particle creation. Even in what we might consider a perfect vacuum, a space devoid of all matter, quantum fluctuations constantly occur. These fluctuations give rise to virtual particles that briefly pop into and out of existence, underlying the inherent uncertainty and dynamism of the quantum world. The Casimir effect provides tangible evidence that empty space isn't truly empty. In this phenomenon, two uncharged metallic plates placed extremely close together in a vacuum are drawn towards each other. This attraction isn't caused by electromagnetism or gravity, but by the quantum properties of the vacuum itself. The restricted space between the plates limits the types of virtual particles that can exist there, creating a pressure difference that pulls the plates together. This effect, predicted by Hendrik Casimir in 1948 and experimentally verified in 1996, demonstrates the real-world consequences of quantum vacuum fluctuations. The Schwinger effect takes the concept of particle creation from nothing even further. When an electric field becomes strong enough, it can transform virtual particle pairs into real particles. Until recently, this was thought to occur only in extreme environments like the vicinity of black holes or neutron stars. However, in a breakthrough experiment, researchers at the University of Manchester observed a version of this effect using graphene. By applying a strong electric field to a graphene-based structure, they witnessed the spontaneous production of electron-hole pairs, analogous to the electron-positron pairs predicted by Schwinger. This achievement brings us closer to understanding some of the most fundamental processes in the universe. Quantum analog systems, exemplified by experiments like the one with graphene, have become powerful tools for investigating exotic physics. These systems employ the same mathematical principles that describe inaccessible physical realms but can be created and studied in a controlled laboratory setting. They allow scientists to explore phenomena that would otherwise be beyond our reach, bridging the gap between theoretical predictions and observable reality. Our current understanding paints a picture of the universe not as matter floating in empty space, but as a complex network of interacting energy fields. These fields create everything we observe, including ourselves. They are in constant motion due to quantum fluctuations, brief changes in energy that resemble ripples in a wave. Even in their lowest energy state, known as the vacuum state, these fields exhibit continuous activity. Pairs of positive and negative particles continually borrow energy from the vacuum, briefly materialize, and then vanish, returning energy to the vacuum. The creation of stable matter particles is actually an exception to this constant flux. It occurs when there's enough energy in the fields to produce particles that aren't immediately annihilated by their antimatter counterparts. This process, while not fully understood, is crucial to the formation of the visible universe we inhabit. While the universe teems with virtual particles and quantum activity, the concept of nothingness isn't entirely dismissed. The nature of the nothingness that may have preceded the Big Bang remains one of the greatest mysteries in cosmology. Moreover, the very notion of nothingness in a quantum universe raises profound philosophical and scientific questions. As we continue to unravel these mysteries, we must embrace the curiosity that drives us to explore and understand the cosmos. Each discovery opens new avenues of inquiry, reminding us of the vastness of what remains unknown. The journey to comprehend the fundamental nature of reality is ongoing, filled with surprises that challenge our preconceptions and expand our understanding of the universe we call home. Music.